Greetings, space nerds. Are you liking this podcast so far? Well, Are We There Yet is supported by listeners just like you. So consider showing your support with a financial contribution to WMFE. You can do that by visiting wmfe.org/support. Your gift helps us better explore exploration. Thanks. From the studios at WMFE in Orlando, Florida, this is the Space Exploration Podcast asking the question, are we there yet? Hi, I'm Brendan Byrne. All right, so if we're going to go on a long-duration mission like one to Mars, we're going to need a few essentials: fuel, food, and water. Now, all of this stuff takes up mass, and mass requires fuel to get it from Earth into space. So what if we could save some mass by recycling some of these things while we're en route to Mars, like water? So think about this. You drink water, your body processes it, and after you drink water, is there a chance we could possibly maybe reuse that? Well, yeah, that's what I'm getting at. And what if astronauts could recycle their urine? Well, they actually do. And my guest right now is working on the technology that turns urine and other liquids like sweat into drinkable water. Now, what goes into recycling this liquid, and what's next for the future of in-flight liquid recycling? Laura Kelsey is the principal investigator and program manager for the Water Recovery Project with Paragon Space Development Corporation, and she's here to shed a bit of light on the subject. Laura, thanks for chatting with me.
Yeah, no problem.
All right, so let's start from the beginning here. When did this idea of recycling astronaut urine come about, and how was it developed?
Yeah, so I think, NASA's been recycling astronaut urine on the space station, I think since the space station has been in operation. However, it hasn't been recovering as much water as needed. And so they've been needing to improve that technology for the past several years. And that's where our technology came in. And we've been developing this water processor for, I think about 4 years ago is probably about when it started. And that's when I got involved with it right from the beginning as well.
Laura, walk me through the process. How does this technology work?
Sure. So as I mentioned before, the space station already has some technology to recover water from urine. But they can't get all of the water. They get about 80% of the water, which seems like quite a bit. And on the space station, that's worked for the past several years. However, that water that they're still losing, which works out to be hundreds and hundreds of liters in a year, that water has to be replaced, and so that has to be currently launched up on different vehicles, and it's very expensive to launch anything into space, really. A really round number is think $10,000 for every pound that you launch into space. So when you're looking at hundreds of liters every year, it builds into the millions of dollars very quickly. So the step that was needed to improve this urine processing was to take the residual, this what is now concentrated urine, which is called brine, and get the remaining water out of that. And that's actually what our technology does. It's a brine processor, so that you can get up to more like 98% of the water out from urine, as opposed to the 80%. So that's not only going to save the space station a lot of money in terms of their launch costs, but is really needed in order to do longer duration missions that aren't dependent on Earth. So, for example, main example being a mission to Mars, which is going to take a couple of years. You can't just send another rocket after your spaceship with more water. You need to recycle as much as physically possible. And so that's what this technology is really enabling, is those future long duration missions.
So what's the technology like on the International Space Station right now that gets that 80%? Is it kind of like just your at-home Brita filter? How are you able to clean it out?
Yeah, not quite. For the urine side of it, they use a process actually called vacuum compression distillation. Basically, they're distilling urine, which means evaporating the water out of it, and when you recondense that water vapor, it's much, much cleaner than your original urine. That's hard to do in space because you can't, it's not like a pot you can put on the stove, and the steam rises and the water stays in the pot like it should. Well, you can't do that in microgravity, or no gravity. So it gets to be a much more complicated system where you actually have this rotating drum in order to separate the phases to keep the urine in one spot and the water vapor in the middle. But the problem is when you're doing that, urine is basically salt water. And once you start getting really concentrated, once you start moving a lot of the water out of it, you start getting like salt depositing onto the surfaces of your equipment. And that basically breaks things. You have to go in there and clean that out. And one of the big problems with urine is that it's hazardous, and not just because it's urine, but there's these chemicals that have to be added to it so that you don't get biological growth. Basically, you don't start getting mold and all of that growing.
So what's the solution then? What are you working on to get it above that 80% efficiency?
We use these special membranes to keep the liquid brine on one side of the membrane, and we allow the water vapor itself can pass through the membrane and then be recovered on the clean side of the membranes. And the unique thing...
So that keeps the equipment clean then, right?
Well, the unique thing is that we actually use the membranes as a bag. So we put the brine inside of these bags that are made for the membranes, and you evaporate all the water out, and then what's left inside is just the really concentrated acid and salts from the urine. And then those are then disposable because they're just made of these lightweight, thin membranes. So now you have a system that is meant to be able to have precipitation, that's the word I was looking for, where you want to be able to pull all the water out and you want it to be solid in the end. And now you have that all contained. So instead of having to go scrape out all this your hardware, you just take this bag out and you go put it in your storage until it's ready to be ejected from the spacecraft.
Now, I've got to ask, what does it taste like when it comes out of the system?
It is, honestly, it's probably better than a lot of your municipal water sources. But it actually goes through a secondary water processor. Basically, in a lot of space, on the space station and baseline for their spacecraft, there's usually a water processor that is actually much more like your Brita water processor. Or if you have a water softener, something that takes like the metals out of your water, that's usually like a ion exchange, and then your like Brita filters are like carbon activated carbon filters, and that really forms the core of like the main water recovery system that's in use on the space station right now. So all of the water on the space station and your spacecraft goes through this like polishing system anyway. So the water that comes out of our brine processor can go directly into that polishing system to come out potable, extremely clean, actually cleaner than a lot of your EPA regulations.
Now, we're not just talking about astronaut urine here. You can use any type of water on the International Space Station, right? Like sweat, gray water, right? You can kind of process all of that.
Sure. Some of those things don't need to go through the more intensive brine processor. For example, sweat, as it is, it gets evaporated, goes into just the atmosphere on the space station. And then really once that's condensed, it's already pretty clean. So that goes straight into your related polishing system. But yeah, there are other water recovery concepts and architectures where you just take all of the water goes into one system, no matter how dirty it is. And that's the thing about the brine processor system is we are literally taking the dirtiest, nastiest water that is produced, that you can get, and turning it into very clean, reusable water. So it can take nearly all water sources on the space station.
Now, is there talk about using that little bit that you can't recover and as you say, you kind of just, throw it out? But is there a way that you can recycle that, maybe not for human consumption or anything like that, but use it for something else on the space station or a deep space craft?
For like deep spacecraft, there's been talk of using something like that for like radiation shielding. So that'd be kind of like what level for the overall entire spacecraft is it usable for? So, but that is one of the ideas, is that the thick, it's almost like kind of a peanut butter consistency, can be used as like this radiation shielding for the crew then.
Huh, that's wild stuff. So tell me about, so Paragon Space Development Corporation won a NASA small business grant. Kind of talk to me about how the development's going, where you are now, and what's still left to kind of increase this efficiency.
Sure. So this started as back in it's called a Phase 1 Small Business Innovative Research Grant, and that was about 4 years ago. And we've gone through Phase 3 of those, and that's been pretty consistently over the last 4 years in some stage of development. So really where we're at now is that we've proven that the technology itself is not only feasible, but it's very successful at recovering a lot of water and producing very clean water from brine, with little contaminants that are moving with the water and into the rest of the cabin environment, and that it can scale up, basically. So we've done it at large amounts of processing of brine that we're starting with. So now we're really taking it from demonstrating it in the laboratory environment to turning it into real flight hardware. So things like, I can make a plastic box that'll work in the lab. You have to make that a little more robust in space, and you want to do things like reducing your weight and reducing your volume and reducing your power and making things ultra reliable. And so we're at that stage. So really taking the concept that's been proven out to this reliable space system and space hardware.
What kind of testing goes into that? Do you just kind of come up with a concept and then fly it up to the ISS, or is there microgravity testing that you put it through? What's the process?
So for this technology, NASA's done a variety of microgravity tests, like smaller scale microgravity tests with membranes, and some with like brine solutions. It's really just like kind of like saltwater solutions, to kind of gain some understanding of how some of these basic technologies will work in space, and how like your salt water acts. It acts very differently in zero gravity than it does on Earth. So there are things like that have been done, that NASA has experience with, and that we're able to leverage. This hardware actually right now is really being developed as a year-long experiment for the space station. So we'll be doing a lot of testing on the ground first, really proving out each of the little components, making sure every individual part works like we think it should, and then making it all, putting it all together, making sure not only that it operates and functions like it should, but that it can also survive in the launch environment. So on your rocket, it can survive when it's in space and being handled by, and that the crew members, the astronauts, are able to do it while in space, because certain things are easy to do when you have gravity, and some things get a lot harder when you don't have gravity. So we're actually demonstrating this technology for a whole year once it's on the space station, during which time the space station gets the added benefit of additional water recovery. And then at the end of that year is when we go, yes, it's great, everything's working well, but you know what? Here's some little tweaks we could do. Here's some things we could improve. And that information is what is going to be used for example, designing the one that would be used to go to Mars. Because the one that's going to Mars, you don't really get chances. You don't really get a second chance to fix that thing. So that's what this year-long demonstration on the space station is. And then once the demonstration period is over, then it just will continue to be operational hardware on the space station. So they get to continue benefiting from the additional water recovery.
Water, an imperative resource to humans if they're going to survive in these long-duration missions. What is it like working on the technology that's going to provide this resource for the people that may one day step foot on Mars?
Yeah, that part's really exciting. It's kind of weird to first think about, oh, I'm working with urine. Why? How is that exciting? That doesn't sound like something I want to do. But when I think about the fact that, hey, this is one of the key technologies that NASA has identified as this is one of the few things that we still need in order to make these kind of missions possible. Makes it really exciting and fun to come to work.
Laura Kelsey is the principal investigator and program manager for the Water Recovery Project with Paragon Space Development Corporation. Laura, thanks for chatting with me.
No problem. It's my pleasure.
That's it for this episode. Support for Are We There Yet comes from the listeners of WMFE. You can follow the show online. We're on Twitter at AWTYMars, or reach out to me in the Twitterverse. I'm at Space Brendan. And leave us a review on iTunes. That's how more people learn about this podcast. Are We There Yet is a production of WMFE. Our theme music was composed by Kevin McLeod. For more space news, visit us online at WMFE.org/space. I'm Brendan Byrne. Thanks for listening.